Okay, good morning, good afternoon, and good evening. So, welcome back to our online class. This is a class for MA 110. So, I'm going to continue on the topic called mathematical induction. I'm going to continue on a topic called mathematical induction. I already made the first part of this topic. So if you didn't do the first part of this topic, I'm advising you go do the first part of the video before you look at this one. So mathematical induction, and remember we are short tutorials. This is short tutorials, and you can reach us on 0964 736805. That is us. So I'm looking at mathematical induction. So just as we said in the previous class, we said the mathematical induction is just the process. This is one of the process of proving a general theorem. We said by definition that this is the process. Interesting. I don't know what has happened. Gone off it. So let me go back. Okay, here we go. So mathematical induction, this is just the process of proving a general theorem or formula. This is what we said in the introduction class. The process of proving a general theorem or formula. So every situation when you've been given every time when you've been given a theorem or a formula, you are being taught to prove by mathematical induction. So this is what we are going to be talking about. We did the first part where we talked about formulas involving summations. So in this mathematical induction, obviously there are a lot of processes in proving if a general theorem or formula do exist or it is true. But with mathematical induction, it's the process of proving a general theorem or formula involving, we can also just try to add that, involving positive integers. So when we talk about positive integers, we're talking about n maybe equals to 1, 2, 3, etc., and the count continues. So we're talking about, we will be proving a general theorem or a general formula with these values of n, where n is a positive integer. So does that formula exist for values of n which are positive integers? That's what we're saying. So we said that the steps involved, there are just about 3 steps. So step number 1, we'll be looking at checking the base step. There are just only 3 steps you're going to encounter when you're proving the mathematical induction. First step, you prove the base step. In the base step here, it is a situation whereby you let n to be equal to 1. And then number 2, you show the inductive step. This is the inductive step. In the inductive step here, we said that this is a situation where you check whether you let n to be equals to k. So if n is equals to k, then it is also true. It is also true for n equals to k plus 1. So these are the major 2 steps which we are using in mathematical induction. And then lastly, once these three steps are done, what do? You can go ahead and conclude that the formula is true. For values of n greater than or equal to 1, because we started from 1, we assumed that n is equal to k. We are simply saying that for n equal to k, then it is also true for n equals to k plus 1. So for all positive values of n, then we have that mathematical formula or theorem to be true. This is what we said in our first meeting, or maybe in our first video of mathematical induction. So next thing here, what we're going to do today, I don't know if I mentioned this. When we talk about mathematical induction in MA 110, we are going to be talking about 3 types of questions which are going to be asked about. So the types of questions, or the types of formulas to prove, or theorems, will be in 3 types. Number 1, we'll be talking about the summation types. I'm sure the summation is what we did in the same video last time. We'll be looking at the summation type of formulas. Then number 2, we'll be looking at the inequality types. So video 1, we talked about the summation type. Inequality, how do you spell inequality? Inequality types of questions. And the last part we'll be looking at is a divisibility type. So we'll be looking at the divisibility type of questions. So with these 3 is what we are going to be checking using mathematical induction to check whether that theorem is true or not. So in this video, which is part 2, I'll be looking at the inequality types of questions in terms of proving by mathematical induction. So we are looking at the inequality types in this video. In the previous video, we talked about the summation types. So the inequality type here, what you need to know, first thing which you need to know, is the transitive rule, or the transitive property. So how does the transitive property state or maybe work? So this is one thing you have to understand. So you'll be having situations where you're trying to compare 3 individuals. So if I'm trying to compare 3 individuals with the transitive property, let's say for example, e.g., we can simply say that A is bigger than B. This is the first statement. The other statement, we can say that B is bigger than C. So if we look at these 2 situations, we are trying to look at 3 people here, 3 individuals. There is A, there is B, and there is C. So in the comparison where we have A being bigger than B, and at the same time B is bigger than C, so through the transitive property, by the transitive rule or the transitive property, we can say that A is bigger than what? Than C. Because this is coming from where? If I was to use inequality expressions, bigger means greater than symbol S. So if A is greater than B, but again we have B being greater than C, this implies that by default, A, if it's bigger than B, where B is greater than C, it means that by default A will also be bigger than C. This is what the transitive property, this is how the transitive property works. So one important thing and one important rule we have to work with in these types of questions is the transitive rule. You have to know it very well. So I'll start with a certain question there. So with this question, we're going to say prove by induction that 2 power n is greater than n for all n greater than or equal to 1. This is what we want to prove. Prove by induction that 2 power n is greater than n for all n greater than or equal to 1. So how do we do that? So number one, first thing, just as I said, I think even in the previous video, when you're proving by induction, you tell them to say, we prove by induction. You tell them, so okay, this is a proof by induction. So if it is a proof by induction, we know that a proof by mathematical induction occurs in terms of two major steps, the base step and the inductive step. So what do we have? We have, we tell them, say, okay, we have 2 power n greater than n. So what do we do? What does the base step say? The base step is simply telling us to let n to be equal to 1, which is our base step. So if n is equal to 1, it means what are we going to have in our theorem or formula? We're going to have 2 power 1 is greater than what? 1. Is this true? Is this true? This is by default a true statement. So the base step, if we let this n to be equal to 1, we're going to have 2 power 1. Obviously 2 power 1 is just a 2, and this is greater than what? 1. It is true that a 2 is bigger than 1, so that is why this is a what? A true statement. You even write to say true statement. This is the first step under mathematical induction. We said that in mathematical induction there are two major steps which show the base step and we show the inductive step. So this which we've shown here is the base step. This is our base step, where n is equal to what? 1. So the next part which you have to show is the inductive step. So the inductive step is, we let this time around, let n be equals to k. This is what we are going to let. So since we are letting n is equals to k, but remember the expression says for n greater than or equal to what? The question was saying the formula proves that 2 power n is greater than n. Prove that 2 power n is greater than 9 for n greater than or equal to 1. So this is what we are going to show. If n is equal to 1, n is equal to k, then we can also replace upper the k for everywhere. Upper the n, everyone is now k. So n is equals to k for k greater than or equal to what? 1. So it means this k which we are replacing is any number which is greater than 1. Obviously, in the first place we said n is equals to 1. So in the second place we can just let n equal to k, where this k is greater than 1 by default. So if this is the case, then what we are going to have is, we have, remember it was 2 power n greater than n. Since we've let n to be equals to k, we are going to have 2 power k is greater than what? K. This is what we are going to have, isn't it? So the inductive step says we assume this to be true, isn't it? So we assume this to be true. So we're going to say we can let this to be our first equation. Then next we let n to be equals to k plus 1. So if we let n to be equals to k plus 1, what are we going to have? if we let n to be equals to k plus 1, then what are we going to have? So we're going to have 2n plus, this is now k plus 1 to be greater than the value of n is k plus 1. We're going to have k plus 1. This is our second equation. So what are we going to do here? The inductive step says that assuming that the formula is true for n equal to k, we need to show that it is also true for n equals to k plus 1. So you write that statement to say assuming it is true for n equals to k, then we need to show that it is true. It is also true for n equals to k plus 1. This is the statement we are going to write there, because this process which we are trying to show here is an inductive step, and the inductive step, it is the one which leads us to our solution to prove that that formula is indeed true. So how are we going to do this? To achieve this, we use equation 1 to show equation 2. So we know what equation 2 is. This is equation 2. We know what equation 1 is. So we're going to manipulate equation 1 to look identical to equation 2. So there's something which needs to be done to equation 1 so that equation 2 can also happen. So grabbing equation 1. So equation 1 is 2 power k is greater than k. And remember, we want something to have something similar to equation 2. And equation 2 does not have 2 power k, but has 2 power k plus 1. So it's up to you now to see what you can do to your left hand side so that you can have an exact thing as 2 power k plus 1. So for me to have a k plus 1 here, what do I do? It means we are going to multiply. This was equation 1, remember. So what do? We multiply 2 on both sides of equation 1. Because when we multiply 2 this side, I'm going to have 2 times 2 power k. It means I'll use the properties of indices to just sum up the powers to have k plus 1. So if I multiply both sides by 2, what am I going to have? I'm going to have 2 multiplied by 2 power k is greater than 2 multiplied by a k this side. So that is why I'm going to have this times that. This is the same as same bases but different powers, because this is power 1. So this is just as good as 2. We just sum up the powers k plus 1, because when you're multiplying two indices numbers having the same bases but different powers, we just maintain one base and sum up the powers. This is greater than 2k. That is what we have. So what do we have here? Remember, recall. I want you to recall something here. Recall that equation 2 is what? 2 power k plus 1 to be greater than k plus 1. This is the comparison we are going to now make. So equation 1 number has led to a 2k plus 1 greater than 2k. This is what we have. So number, here we have 2k plus 1 greater than k plus 1. Here we have 2k plus 1 greater than 2k. So it means our comparison now needs to make this 2k and this 2k. We want to, this 2k and this k plus 1. We need to compare them and see who is bigger than the other. Because the left hand side, obviously, we have the same thing, which is okay. But the contradiction is on the right hand side. So the question is, who is bigger than the other, 2k and k plus 1? So what do we do in the comparison? We see that, so if we compare, we can see that if you let any number of your solitudes be k, let's say k is equals to 3 or k is equals to 4. So if k is equals to 4, you're going to have 2 times 4, you have 8 here. If k is equals to 4 here, this will be 4 plus 1, you have 5 there. So who is bigger than the other? You can see that, we can see that 2k is bigger than k plus 1. How is that true? Because if we take any number of our choice here to be 4, for example, e.g. k is equals to 4, we're going to have 4 times this to be equals to 8, greater than 4 plus this to equal to 5. This is true. That is why we have 2k to be greater than k plus 1. So, by the transitive property, what am I having? We have a situation where 2k plus 1 is bigger than 2k, and the same 2k is bigger than k plus 1 from this situation. Hence, by transitive rule, the transitive rule, since this is bigger than that and that is bigger than that, it means the first one is more bigger than what? The last one. So by the transitive rule, we can say that 2k plus 1 is by default greater than what? K plus 1, which this gives us the second equation. Hence, with this done, therefore, with this done, we can conclude that the expression we had to say 2n is greater than n is indeed true for n greater than or equal to what? 1. And you are done. Because by the inductive step, it has been shown that equation 2 is true. So assuming that n is equals to k, it is also true for n equals to k plus 1. This is true, and you are done. So remember that there are always 2 steps to follow: the base step and the inductive step. The inductive step, you show that when n is equals to k, then it is also true for n equals to k plus 1. This is on the inductive step, which you're supposed to show. Once this is shown, you can conclude that the formula or the theorem is true for all n values. Let's look at the second question. Let's look at the second question. The second question says, we are going to prove that 3 power n is greater than 2n plus 1 for n greater than 1. We are trying to prove this. Remember the steps. The steps are, number 1, we prove by induction. That's the first thing. Sure, we say, what method are we using here? We are proving by induction. So in the proof by induction, the first thing we are going to do, we let n to be equal to what? 1. That's the base step. Let n to be equals to 1. If I let n to be equals to 1, what is my left hand side? We are going to have 3 power 1 in the left hand side. What is the right hand side? We are going to have 2 multiplied by 1 plus 1. Is it true? So this is 3 power 1, 2 multiplied by 1 plus that. So this will lead us to what? This will be 3 greater than 2 plus 1, which is a 3. This base step is giving us a 3 equal to 3. Now, to just spice up things, because with this we cannot conclude that the base step is true. We continue. Now let's go back. The question says for n greater than 1, it does not mean that for n is greater than or equal to 1. So this means that here we have to pay attention to what has been given here. It says prove that 3 power n is greater than 2n plus 1 for n greater than 1 and not n greater than or equal to 1. These two are two different statements. It is not this, it is this. So it means the best step will not be n equal to 1. Pay particular attention to what has been given here. So the best step will not be n equal to 1 because the best, if we use n equal to 1, the inequality does not hold. This is just 3 greater than 3. This is not greater than 3. It is equal to 3. So it means that using the best step here will be appropriate to use letting n to be equals to 2 and not this. This will not be the best step. This will not be the best step since n is greater than 1 and not n greater than or equal to 1. So we pay particular attention to that. So we let n to be equal to 2. This will be our best step. So if we let n to be equal to 2, what is going to happen? If we let n to be equal to 2, what is going to happen? We're going to have 3 power n, which is squared, is greater than 2 multiplied by 2 plus a 1. So the left hand side, 3 squared, this is a 9, greater than, this will be 4 plus 1, which is equal to 5. Is it true that 9 is greater than 5? Yes, it is true. This is a true statement. This is a true statement. And you are done. The best step. Next, after the best step, what do we do? The inductive step, where we do what? We let n to be equals to k. So if I let n to be equal to k, what is going to happen? If I let n to be equal to k, what is going to happen? I'm now going to have 3 power k to be greater than 2 multiplied by k plus 1. And we'll take this as our equation 1. That's what we're going to have. And then next, we will let n to be equals to k plus 1. So if I let n equals to k plus 1, what is going to happen? I'm going to have 3 multiplied by k plus power of k plus 1 is greater than 2 multiplied by k plus 1 outside this plus 1. Simplifying this, we're going to have 3k plus 1 is greater than 2k plus 2 plus 1, so that this leads us to a 3k plus 1 is greater than 2k plus 3, and this becomes our second equation. So if this is the idea and this is the issue we have here, with the inductive step, we need to show. So what are we going to say? We are simply saying, assuming the statement is true for n equals to k, we need to show that it is true for n equals to k plus 1 also. So to achieve this, we use equation 1 to obtain equation 2. So what was equation 1? Equation 1 was 3 power k to be greater than 2k plus 1. This was equation 1. So So we're going to use this equation to obtain equation 2. So equation 2 first it is 3 power k plus 1. So we manipulate the right hand side so that we can also have power k plus 1. This can only happen if you multiply both sides by the same 3 power 3 as a base. So what am I going to have? Multiply 3 on both sides of the equation 1, so that we can have 3 multiplied by 3 power k is greater than 3 multiplied by 2k plus 1, so that you can have same bases, different powers, we just sum up the powers. We're going to have k plus 1 is greater than 3 in there, and this is 6k plus 3. This is what I'm going to have. So number, we now do a comparison. So what is going to happen here? Recall, equation 1 was what? Equation 2. Equation 2 was 3k plus 1 is greater than, what was equation 2? 3k plus 1 is greater than 2k plus 3. This was equation 2. Now we're trying to compare the two guys. What we have now is, but we have 3k plus 1 greater than 6k plus 3. So what is our issue? We have to compare these two right sides to see which one is bigger than the other. So to do this, we're going to say we see that we can see that 6k plus 3 is indeed bigger than 2k plus 3. Mathematically, you can even say that. Because if I was to take any number k, e.g. let k to be equals to 2, if k is equals to 2, we're going to have 6 multiplied by 2 plus 3 this side, and 2 multiplied by 2 plus 3 this side. This will be 6 times 2 is what? Is it 12 plus 3? But this one will be 4 plus 3. 12 plus 6 is a 15, but this is a 7. This is true. So it means 6k plus 3 is indeed greater than 2k plus 3. So what we are having here is 3k, which we have been formed 3k plus 1, which is greater than 6k plus 3. We have that this 6k plus 3 is also bigger than 2k plus 3. Therefore, by transitive rule, by the transitive rule, 3k plus 1 is also bigger than what? 2k plus 3. This is a true statement. So if it is a true statement, hence the formula or the theorem, the expression 3 power n greater than 2n plus 1 is true for n greater than 1, and you are done. So this is how you will be solving questions regarding involving inequality types. So this is how you'll be solving questions involving inequality types. So whatever inequality question you are going to have, you solve it in that manner. So the task I'm going to leave you with here will be, can you prove the following statement? So prove for 4 power n to be greater than or equals to 4n. Can you also prove for b 2 power n to be greater than n? I think we've solved this one. And then can you also prove for c where n squared is greater than or equal to n? So these ones are the ones I've added, and then with 5 there or 4, you can also prove 5 power n is greater than or equal to 5n minus 1. So prove by induction. Prove by induction the following. Prove by induction the following. So you can solve those ones with the way we've just done it for you, and send your solution to our contact 0964 736805. Mr. Suit. And have a flavored week ahead. Thank you.